What if I told you that right now, at this very moment, somewhere in the depths of the cosmos, time itself is bending, not metaphorically, literally. Imagine a place where gravity is so intense that it warps the fabric of reality, where a single hour could stretch into years, or where the past and future might collide in ways that defy everything we think we know. This isn't science fiction, it's the mind-bending reality of black holes and the tantalizing possibility of time travel. These two cosmic mysteries have captivated scientists, storytellers, and dreamers for generations, and today we're diving headfirst into 30 of the most incredible theories that bridge them. Buckle up, this is going to be a journey unlike any other. Think about the classic grandfather paradox. If you traveled back in time and accidentally prevented your own birth, how could you exist to make the trip in the first place? It's a puzzle that stumped physicists for decades, yet it's just the tip of the iceberg. Black holes add another layer of wonder. These cosmic monsters don't just swallow light, they twist spacetime itself into knots. What happens if you cross the event horizon? Could a black hole be a gateway to another universe or even a different era? The answers might lie in theories that sound like they're ripped from the pages of a fantasy novel, except they're rooted in real, cutting-edge science. From wormholes to quantum entanglement, from Hawking radiation to the holographic principle, we're about to explore ideas so strange they'll make you question the very nature of reality. This isn't just about equations or abstract concepts, it's about the human drive to unravel the universe's greatest secrets. Every theory we'll uncover is a testament to our curiosity, our refusal to accept that some questions are unanswerable. Whether you're a casual stargazer or someone who devours every documentary on astrophysics, what you're about to hear will stretch your imagination to its limits. So take a deep breath and prepare to venture beyond the edges of known science. By the time we're done, you'll never look at time or the night sky the same way again. Einstein's theory of general relativity didn't just change our understanding of gravity, it shattered our perception of time itself. Picture this: the closer you get to an object with immense gravity, like a black hole, the slower time ticks for you compared to someone far away. It's not science fiction, it's a fundamental prediction of relativity, and we've actually seen it happen. Take the famous twin paradox. If one twin rockets off into space at near light speed while the other stays on Earth, the traveling twin would return younger than their sibling. But you don't need a spaceship to witness time dilation. Even the GPS satellites orbiting Earth have to account for it. Their clocks tick ever so slightly faster than those on the ground because they're farther from Earth's gravity. Without these adjustments, your navigation would be off by miles within minutes. Now, imagine standing near the edge of a black hole, where gravity is so extreme that time doesn't just slow, it warps beyond recognition. To an outside observer, your clock would appear to freeze as you approach the event horizon. From your perspective, though, time would feel normal, while the rest of the universe would seem to speed up in a dizzying blur. This isn't just theoretical. Black holes like Sagittarius A at the center of our galaxy are natural laboratories for these mind-bending effects. The closer you get, the more time stretches, bending like taffy pulled to its limit. But here's where it gets even stranger. If you could somehow hover just outside a black hole's event horizon, say, for a few hours and then return to Earth, you might find decades or even centuries had passed for everyone else. It's a one-way trip into the future, no DeLorean required. This drastic time dilation isn't just a quirk of physics, it's a glimpse into how malleable the universe really is. And if black holes can warp time to this degree, who's to say they couldn't twist it into a gateway, or even a loop? That's a question Einstein's equations leave tantalizingly open. Wormholes sound like something straight out of a sci-fi blockbuster, a hidden tunnel through the fabric of spacetime, connecting two distant points in an instant. But what if these cosmic shortcuts aren't just fantasy? The math actually supports their existence. Renowned physicist Kip Thorne laid the groundwork for this idea, showing how a traversable wormhole could, in theory, link far-flung corners of the universe or even different eras. Imagine stepping through a doorway near Earth and emerging near a star thousands of light years away, or perhaps in a completely different time. The implications are staggering. But here's the catch: keeping a wormhole stable enough to travel through would require something called exotic matter, a substance with negative energy density. That's not just rare, it defies our everyday understanding of physics. Exotic matter would have to push against gravity, propping the wormhole open like scaffolding to prevent it from collapsing the moment anything tries to pass through. So far, we've never observed this mysterious material in nature, and creating it in a lab remains a distant dream. Yet, the equations suggest it's possible, leaving the door cracked open literally for future discoveries. This concept isn't just confined to textbooks. You've probably seen it brought to life in films like Interstellar, where a wormhole near Saturn becomes humanity's lifeline to a new home. While Hollywood takes creative liberties, the movie's depiction was shaped by Thorne's own calculations, blending science with spectacle. It's a reminder that these ideas, no matter how outlandish they seem, are rooted in real theoretical work. And if wormholes do exist somewhere in the cosmos, they might not just be shortcuts through space, they could be bridges through time itself. Einstein's equations hold a strange secret: paths through spacetime that loop back on themselves like cosmic Möbius strips. These are closed time-like curves, theoretical highways where you could travel into the past without ever leaving the present. One of the earliest examples came from mathematician Kurt Gödel, who showed that in a universe filled with rotating matter, time itself could twist into circles. Picture a vast cosmic whirlpool where following the right path might bring you back to your own departure point, like walking far enough in one direction on Earth only to return where you started, but with time instead of space. The implications are dizzying, but here's where Russian physicist Igor Novikov stepped in with a crucial safeguard: the self-consistency principle. It states that any actions taken along a closed time-like curve must logically align with events that already happened. No grandfather paradox is allowed. If you tried to alter the past in a way that created a contradiction, the universe would somehow correct the discrepancy. Think of it like a cosmic editor. Your time-traveling meddling couldn't rewrite history, only fulfill what always was. For instance, if you traveled back to prevent a famous inventor's birth, you might instead inadvertently ensure the events leading to their existence played out exactly as recorded. This isn't just speculative philosophy. Modern research suggests such curves could form around rapidly spinning black holes or within hypothetical structures like Tipler cylinders, massive, infinitely long tubes of dense material spinning at nearly light speed. The energy required makes them implausible with current technology, but their mathematical existence hints that time loops might be woven into the fabric of reality itself. And if closed time-like curves do exist, they wouldn't just challenge our understanding of cause and effect, they'd force us to reconsider whether the future is truly unwritten or if every moment is already locked in place, waiting to be discovered. Black holes have long been thought of as cosmic vacuums. Once something crosses the event horizon, it's gone forever. But Stephen Hawking turned that idea on its head with a revolutionary discovery: black holes aren't entirely black. In fact, they glow, not with visible light, but with a faint whisper of radiation, Hawking radiation, that carries energy away from the black hole, slowly causing it to shrink and eventually evaporate. This revelation came from combining quantum mechanics with general relativity, two frameworks that usually refuse to play nice. Here's how it works: empty space isn't really empty. At the quantum level, particles and their antiparticles constantly pop into existence, borrowing energy from the vacuum before annihilating each other in a flash. Normally, this happens too quickly to notice, but near a black hole's event horizon, things get interesting. If one of these virtual particles falls into the black hole while its partner escapes, the black hole loses a tiny bit of mass in the process. Over unimaginable stretches of time, trillions upon trillions of years for a typical black hole, this gradual leakage adds up, leading to the black hole's eventual demise. This isn't just a quirky side effect, it sparks a profound mystery known as the information paradox. In quantum mechanics, information, the fundamental details of every particle's state, can't be destroyed. But if a black hole evaporates completely, what happens to all the information it swallowed? Does it vanish forever, violating quantum laws, or is it somehow encoded in the Hawking radiation, scrambled beyond recognition? Physicists still wrestle with this puzzle, and its resolution could reshape our understanding of reality itself. The paradox also ties into the arrow of time, why we remember the past but not the future. Black hole evaporation introduces a one-way process. Once the radiation is gone, there's no reversing it. That irreversibility might hold clues about why time flows in a single direction, even though the fundamental laws of physics work just as well backward as forward. Some theories suggest that the information isn't truly lost but stored in a hidden layer of the universe, like cosmic fine print waiting to be decoded. Hawking radiation challenges everything we thought we knew about black holes. They're not eternal prisons, they're ticking clocks, fading into oblivion one particle at a time. And in their slow decay, they might be whispering the universe's deepest secrets about time, information, and the very fabric of existence. Frank Tipler's rotating cylinder is one of those ideas that sounds impossible until you crunch the numbers. Imagine a structure so massive and dense, stretching infinitely long through space, spinning at nearly the speed of light. According to Tipler's calculations, this colossal cosmic drill wouldn't just distort space, it would twist time itself into a loop. If you followed a precise spiral path around its surface, you could theoretically travel backward through time, returning to a moment before you even began your journey. It's a concept that dances on the edge of science fiction, yet it emerges directly from Einstein's equations. The key lies in frame dragging, an effect where a massive rotating object literally drags spacetime along with it, like a spoon swirling honey. Earth does this on a tiny scale. Satellites in orbit have to account for minuscule shifts caused by our planet's rotation. But scale that up to a cylinder with the mass of several suns, spinning fast enough to blur the line between matter and energy, and the effect becomes extreme. Spacetime wouldn't just bend, it could tie itself into a knot, creating a closed timelike curve where the end of your journey meets the beginning. There's a catch, of course. For this to work, the cylinder must be infinitely long. Any realistic finite version would tear itself apart under the unimaginable stresses, or require physics-defying materials to hold its shape. And then there's the energy problem. Accelerating something that massive to near light speed isn't just impractical, it's beyond anything our civilization could fathom achieving. But here's what makes Tipler's idea fascinating. It's not ruled out by the laws of physics as we know them. It lives in that tantalizing gray area where theory hasn't yet yielded to impossibility. Think of it like a cosmic version of a record player. If you could place a needle on the edge of this spinning cylinder and trace its path, you'd eventually return to your starting point, but not just in space. Time itself would loop, stitching the future to the past. This isn't just a mathematical curiosity, it challenges our deepest assumptions about causality. If such a structure existed, would the universe enforce consistency, as Novikov suggested? Or could you actually alter events in ways that ripple unpredictably through history? Tipler's cylinder forces us to confront these questions head-on, with no easy answers in sight. While we'll likely never build such a monolith, the thought experiment remains vital. It pushes general relativity to its limits, revealing just how malleable time might truly be under the most extreme conditions. And who knows, perhaps somewhere in the universe, under laws we've yet to discover, nature has already forged its own versions of these impossible machines, spinning silently in the dark, weaving time into shapes we can scarcely imagine. Quantum entanglement is one of those phenomena that makes even seasoned physicists pause. Two particles become mysteriously linked, instantly influencing each other's states no matter how far apart they are, faster than light, defying classical notions of cause and effect. This spooky action at a distance, as Einstein famously called it, doesn't just challenge our understanding of space, it hints at a deeper, stranger relationship with time itself. Imagine flipping a coin in New York and another in Tokyo, and every time yours lands heads, the other always lands tails, no delay, no signal passing between them. That's entanglement in a nutshell, and it raises a tantalizing question. If particles can communicate instantaneously across space, could they somehow bypass the usual rules of time too? Enter the quantum eraser experiment, a mind-bending twist on this idea. In one version, scientists send entangled particles toward detectors, but with a clever trick. The choice to measure or erase information about their paths is made after the particles have already been detected. Astonishingly, the results change retroactively, as if the particles knew whether their paths would be revealed or concealed in the future. It's like mailing a letter that adjusts its contents based on whether you decide to open the envelope weeks later. This isn't just a quirk of the lab, it suggests that quantum systems might not settle into a definite state until influenced by future observations, blurring the line between past and present. Now stretch this idea further. If entangled particles can seemingly respond to events that haven't happened yet, could we harness this to send messages backward in time? Some theorists speculate that entanglement might create temporal loopholes, tiny cracks in causality where information slips through the usual forward march of time. Think of it as a cosmic game of telephone where the message arrives before it's sent. Of course, there's a catch. Any attempt to exploit this for time travel would likely scramble the information into randomness thanks to quantum unpredictability. You might receive a signal from the future, but decoding it could be like listening to a radio tuned to static. The implications ripple into black hole physics too. Near an event horizon where time stretches to a near standstill, entangled particles could become tangled across time itself. One particle might fall into the black hole while its partner remains outside, creating a bridge between moments that no longer align. This could theoretically allow information to escape the black hole's grip, not by climbing back out, but by hopping through a quantum backdoor woven into the fabric of time. Skeptics argue these ideas push speculation to the edge, and they're right. No one's building a time machine with entangled particles anytime soon. But the mere possibility forces us to confront a profound truth. At the quantum level, time might not flow the way we experience it. It could be more like a vast, interconnected web where cause and effect aren't straight lines but a tangle of threads waiting to be pulled. And if that's the case, the universe might be far stranger and far more malleable than we ever dreamed. Einstein's theory of relativity sets a cosmic speed limit. Nothing can travel faster than light. But what if you didn't have to move faster than light to outpace it? That's the radical idea behind physicist Miguel Alcubierre's warp drive. Instead of propelling a ship through space, his solution was far more elegant: manipulate spacetime itself. Picture a surfer riding a wave, carried forward not by their own effort but by the motion of the water beneath them. Alcubierre's warp drive works similarly, creating a bubble of distorted spacetime that carries everything inside it at incredible speeds without ever locally exceeding light speed. The mechanics are mind-bending. Ahead of the bubble, spacetime compresses, pulling distant points closer together. Behind it, spacetime expands, pushing the starting point farther away. Inside the bubble, space remains flat and calm, like the eye of a hurricane. Passengers wouldn't feel acceleration or g-forces, just stillness, even as the bubble hurtles through space. It's a loophole in relativity's rules. While nothing can move through space faster than light, spacetime itself has no such restriction. The universe's fabric can stretch and squeeze at any speed. But there's a catch. To create this warp bubble, you'd need something called negative energy, a theoretical form of matter with repulsive gravity. Think of it like anti-glue, pushing space apart instead of pulling it together. Negative energy isn't just rare, it might not even exist in forms stable or abundant enough to power a warp drive. Quantum mechanics allows for fleeting glimpses of it, like the Casimir effect, where empty space between two plates briefly generates negative pressure. But scaling that up to Alcubierre's vision would require technologies far beyond our grasp. Another hurdle is the sheer energy cost. Early estimates suggested the drive might need the equivalent of Jupiter's mass converted to energy, a practical impossibility. Later refinements hinted at smaller, more manageable amounts, but the challenge remains astronomical. And then there's the radiation problem. Particles caught at the warp bubble's edges would accumulate catastrophic energy, potentially obliterating anything at the destination upon arrival. Yet, despite these obstacles, the idea persists not as blueprints for an imminent engine, but as a tantalizing what-if. NASA Eagleworks Lab has even explored miniature versions in experiments, testing whether microscopic warp effects might be detectable. Science fiction loves the concept too, from Star Trek's iconic warp speed to Interstellar's gargantua black hole, where space-time distortions become a narrative tool. Alcubierre's warp drive forces us to rethink not just propulsion, but the nature of space and time. It's a reminder that the universe's rulebook might be more flexible than we imagined, and that the boldest ideas often live in the gap between impossible and not yet. Whether warp travel ever becomes reality, it serves as a beacon. Sometimes the fastest way forward isn't to push harder against the limits, but to find a way to bend them. Crossing a black hole's event horizon isn't just a point of no return. It could be the ultimate time trap. Picture this: as you approach the edge, time distorts so severely that seconds stretch into eternities. But what happens after you cross? The math gets even wilder. Enter Penrose diagrams, a brilliant way to visualize space-time around black holes without the crushing weight of complex equations. These diagrams flatten the universe's geometry into a two-dimensional map, where light travels at 45-degree angles and infinity fits neatly at the edges. Here's where it gets mind-bending. On a Penrose diagram, the event horizon isn't just a line, it's a boundary where space and time switch roles. Outside the horizon, you can still move forward or backward in time, just like we're used to. But step inside, and suddenly every path leads inexorably toward the singularity. Time, as you know it, ceases to exist. Your future isn't just predetermined, it's geometrically inevitable. The diagram reveals something even stranger. If you could hover just inside the horizon, you'd find yourself caught in a loop where time circles back on itself endlessly. It's like being strapped to a carousel spinning at the speed of causality, forever completing the same orbit without escape. This isn't science fiction, it's the grim reality of infinite time dilation. To an outside observer, you'd appear frozen at the horizon, your image redshifting into oblivion as time grinds to a halt. But from your perspective, the universe outside would accelerate into a blur, stars aging and dying in moments. The deeper you fall, the tighter time spiral becomes, until the singularity crushes you into a point where physics itself breaks down. Could this loop be harnessed as a time machine? Hypothetically, yes, if you could survive the tidal forces. A black hole's spin might carve a narrow corridor where closed timelike curves form, offering a precarious path to the past. But here's the catch: any attempt to exploit this would require threading a needle through a cosmic hurricane. One miscalculation and you're shredded into atoms, or worse, trapped in a cycle where cause and effect unravel like a Möbius strip. Penrose diagrams don't just illustrate doom, they reveal a haunting beauty in the universe's design. black holes aren't just destroyers, they're time's most extreme sculptors, bending reality into shapes we're only beginning to fathom. And while we may never plunge into one to test these ideas, their mathematics whispers a tantalizing truth. Somewhere in the cosmos, time might not flow, it folds. The idea of parallel universes might sound like pure fantasy until you hear the math behind it. The many worlds interpretation of quantum mechanics doesn't just suggest alternate realities exist, it insists they must. Every quantum decision, every tiny fluctuation, spawns a new branch in the cosmic tree, creating infinite universes where every possible outcome plays out. Now imagine weaving this into the fabric of time travel. Suddenly, the grandfather paradox isn't a paradox at all, it's just the birth of a fresh timeline where history takes a sharp turn. Think of it like a choose-your-own-adventure book where every decision splits the story. If you traveled back and prevented your grandfather's marriage, you wouldn't erase your own existence. Instead, you'd simply step into a new branch where your grandfather's life took a different path, and you'd exist in the original timeline untouched. No contradictions, no unraveling reality. The universe wouldn't need to fix anything. It would just keep branching, endlessly accommodating every possibility. This radical idea comes from physicist Hugh Everett, who saw quantum mechanics differently. While others struggled with the collapse of probabilities into a single outcome, Everett argued, what if nothing collapses? What if every outcome happens but in separate, non-communicating worlds? It's a perspective that turns time travel from a logistical nightmare into a question of navigation. The challenge isn't avoiding paradoxes, it's charting a course through the multiverse's infinite possibilities. Black holes add another layer to this. If a black hole's singularity doesn't destroy information but instead funnels it into a new universe, as some theories suggest, then falling into one might not mean death, it could mean rebirth in a parallel reality. Your timeline here would end, but another version of you in another branch of the multiverse might emerge somewhere entirely new. It's a dizzying thought, black holes as cosmic turnstiles, rotating not just space but destiny itself. Critics argue the many worlds interpretation is untestable. How do you prove the existence of universes you can't observe? But supporters counter that it's the most elegant way to resolve quantum weirdness without adding extra rules. And if they're right, time travel might not be about changing this world. It could be about stepping sideways into another one, where history unfolded just differently enough to make the impossible real. So the next time you wonder what might have been, remember, somewhere out there in the vast fractal of the multiverse it is. Every choice, every chance, every twist of fate is playing out in another corner of existence. And if we ever unlock the secrets of time travel, we might not just revisit our past, we could explore the infinite roads not taken. Cosmic strings sound like something straight out of mythology, infinitely thin threads of pure energy, thinner than an atom yet dense enough to warp spacetime itself. These theoretical relics from the early universe, if they exist, could be the ultimate cosmic shortcuts, bending reality into loops and knots with a mere flicker of vibration. Picture two of these strings intersecting or vibrating in just the right way, twisting space-time into a closed loop, a natural time machine forged by the universe's own hand. The math behind this is astonishing. Unlike black holes or wormholes, cosmic strings don't require exotic matter or infinite energy. Their sheer density does the work. A single string under tension could curve space-time so sharply that traveling around it would send you back to your starting point, not just in space but in time. It's like walking in circles around a pole, except each full revolution takes you one step further into the past. The faster you move, the further back you go. Two strings crossing could create a double helix of twisted spacetime, where threading the needle between them might catapult you across centuries in an instant. But how would this work in practice? Imagine a spaceship navigating near a vibrating cosmic string. As the string oscillates, it generates gravitational waves that ripple through spacetime, opening temporary corridors where the usual rules of cause and effect don't apply. If the ship's path aligns perfectly with these ripples, it could emerge at a point in time before it even began its journey. The key word here is perfectly. Cosmic strings are unforgiving. A slight miscalculation could fling you into deep space or trap you in a time loop, reliving the same moment for eternity. The wildest part, these strings might already be out there. Some theories suggest they formed fractions of a second after the Big Bang, when the universe was a seething cauldron of symmetry breaking. As the cosmos expanded, these strings could have stretched across unimaginable distances, forming a vast, invisible network of spacetime fault lines. Detecting them would be like finding spider silk stretched across a galaxy, nearly impossible, but not inconceivable. Some scientists propose looking for their gravitational fingerprints in the cosmic microwave background or the lensing of distant starlight. What makes cosmic strings so compelling is their simplicity. They don't require black holes crushing gravity or warp drives exotic physics. They're elegant, almost minimalist, a twist here, a vibration there, and suddenly time itself becomes a playground. Of course, the universe rarely makes things easy. The energy scales involved are beyond anything we can replicate, and the precision needed to harness these loops borders on fantasy. But the fact that spacetime can bend this way, that the equations allow it, means the universe might already have built its own time machines. We just have to learn how to find them. The holographic principle turns our intuition about reality inside out, literally. Imagine taking every piece of information in your three-dimensional world, the texture of your skin, the sound of your voice, even the memory of your first kiss, and compressing it onto a flat, two-dimensional surface without losing a single detail. Sounds impossible, right? Yet this is exactly what physicists like Leonard Susskind and Gerard T. Hooft propose happens at the edge of a black hole. The event horizon, they argue, isn't just a boundary, it's a cosmic hard drive, etching everything that falls in onto its surface like data encoded on a holographic plate. Here's where it gets even stranger. If the holographic principle holds, our entire perception of time as a flowing, linear force might be an illusion, a side effect of how this encoded information interacts. Think of it like watching a movie. The film itself is just static frames on a flat strip, but when played, our brains stitch those frames into motion. Similarly, time could emerge from deeper, timeless patterns written on the universe's boundary. Black holes become the ultimate test case. As matter crosses the horizon, its three-dimensional structure might dissolve into quantum bits painted onto a two-dimensional surface, with time itself arising from how those bits evolve. This idea didn't come from nowhere. It sprouted from the black hole information paradox, the puzzle of how information swallowed by a black hole could ever escape. The holographic principle offers an elegant solution. The information isn't lost, it's smeared across the horizon like ink on parchment, preserved in a form we don't yet fully understand. Experiments with quantum gravity even suggest that spacetime itself might be pixelated at the tiniest scales, built from discrete chunks of information the way a digital image is made of pixels. If so, the smooth flow of time we experience could be the macroscopic shimmer of these underlying bits flipping states. What does this mean for time travel? If time is emergent rather than fundamental, manipulating it might require rewriting the code at reality's base layer. A black hole's horizon, acting as a natural hologram, could theoretically store timelines like overlapping projections. Falling into one might not erase you, it could translate you into another frame in the cosmic film where time runs backward or loops. The catch, decoding or influencing this process would demand mastery over quantum gravity itself, a frontier we've barely begun to explore. The holographic principle doesn't just redefine black holes, it reshapes our place in the universe. We might be living inside a vast, multidimensional projection, where time is less a river and more a flickering shadow on the walls of something far deeper. And if that's true, the key to unlocking time's secrets could lie not in chasing clocks, but in learning to read the universe's hidden script. Time crystals sound like something ripped from the pages of a pulp sci-fi novel, but they're very real, and their implications for time manipulation are staggering. Unlike ordinary crystals where atoms arrange themselves in repeating patterns in space, time crystals exhibit structure that repeats in time. Imagine a clock that ticks forever without any energy input, or a dance where the steps loop indefinitely without the dancers ever tiring. That's the essence of a time crystal, a system that breaks time symmetry, oscillating between states in a never-ending cycle dictated not by external forces, but by the universe's own quantum rules. The story begins with Nobel laureate Frank Wilczek, who first proposed the idea in 2012. At the time, physicists dismissed it as impossible, a violation of thermodynamics since perpetual motion machines can't exist. But Wilczek wasn't describing a machine. He was pointing to a loophole in how quantum systems behave. In 2017, two separate teams of scientists brought time crystals to life in labs, using chains of ions or defects in diamonds, chilling them near absolute zero and nudging them with precise laser pulses. The result, a quantum choreography where the system ticks at a rhythm slower than the laser's pulse, as if resisting the push of time itself. Here's where it gets even weirder. Time crystals don't just repeat, they remember. Flip the system's state and it retains a kind of quantum memory of its past oscillations, a property that could revolutionize computing. But the real mind-bender is their potential to create microscopic time loops. In certain configurations, particles within a time crystal could effectively rewind their own quantum states, retracing their steps like a film played backward. It's not time travel in the classic sense, but it's disturbingly close. A self-contained loop where cause and effect blur, and the arrow of time bends into a circle. Critics argue these loops are too fragile to harness, vanishing the moment outside interference creeps in. Yet the mere existence of time crystals proves that time, long assumed to be an immutable backdrop, can be fractured into repeating patterns under the right conditions. If we could scale these loops, perhaps by entangling arrays of time crystals, we might one day engineer pockets of spacetime where the usual rules don't apply. For now, time crystals remain lab curiosities, flickering in ultra-cold vacuums, but they're a beacon illuminating a radical truth. Time isn't just something we move through. It's something we might, one day, learn to fold. Stephen Hawking wasn't just a pioneer of black hole physics, he was also a cosmic traffic cop, laying down the law to prevent time travelers from wreaking havoc on history. His chronology protection conjecture is essentially a bold claim. The universe has built-in safeguards to stop paradoxes before they start. Think of it like a cosmic immune system. Any attempt to warp time into a loop would trigger quantum effects that automatically correct the anomaly, snapping reality back into line. Hawking once joked that the absence of tourists from the future was strong evidence his conjecture was right. If time travel were possible, he argued, we'd be drowning in historians eager to document our era firsthand. The mechanism behind this isn't some mystical force, it's rooted in quantum field theory. Imagine trying to create a time loop by focusing an incredibly intense beam of light onto a single point in space. As the energy builds, virtual particles, those fleeting quantum fluctuations, would start popping into existence with enough force to destabilize the loop before it could form. It's like trying to build a house of cards in a wind tunnel. The universe's quantum turbulence would knock it down before the structure could hold. Hawking likened this to a time police enforcing causality, ensuring that cause always precedes effect, no matter how cleverly you try to bend the rules. This idea didn't emerge in isolation. It's a sibling to Penrose's cosmic censorship hypothesis, which suggests singularities. Those infinitely dense points at the hearts of black holes must always be hidden behind event horizons. No naked singularities allowed. The universe keeps its most dangerous toys locked away. Similarly, chronology protection implies time travel's destructive potential is too great to leave unregulated. The laws of physics might literally rewrite themselves in real time to prevent paradoxes, like a computer program that patches its own glitches before they crash the system. But here's the twist: not all physicists buy this cosmic veto. Some argue quantum mechanics might allow time loops under specific, extreme conditions. After all, particles routinely tunnel through barriers they shouldn't cross, and entangled particles seem to flout classical limits. Could time travel be another quantum exception, lurking in the margins of what's possible? Hawking's conjecture remains just that, a conjecture. Until we uncover a full theory of quantum gravity, we won't know if the universe plays hardball with time travelers or leaves the door cracked open for the boldest explorers. What makes this idea so compelling isn't just the science, it's the philosophical weight. If Hawking was right, causality isn't just a human concept, it's woven into the fabric of reality, guarded by quantum sentinels. Time might bend, but it refuses to break, and whether that's a cosmic safety net or a challenge waiting to be overcome, one thing's certain: the universe takes its history seriously. If black holes are the universe's ultimate vacuum cleaners, relentlessly swallowing everything in their path, then white holes are their cosmic opposites, theoretical geysers spewing matter and energy outward with unstoppable force. While no one has ever observed one, the equations of general relativity allow for their existence, painting them as black holes running in reverse. Think of it like pressing rewind on a video of a black hole's life. Instead of matter disappearing beyond the event horizon, it comes erupting back out as if time itself has flipped direction. What makes white holes so fascinating isn't just their defiance of black hole behavior, it's their potential connection to the birth of the universe. Some theorists speculate the Big Bang itself could have been a white hole event, a cataclysmic outburst of spacetime and energy from a singularity. In this view, our entire cosmos might be the other side of a black hole from some unknowable parent universe, its contents ejected in a fiery rebirth. It's a dizzying idea. Every galaxy, star, and planet could trace its origins to a white hole's explosive refusal to let anything stay trapped forever. But there's a catch. White holes violate the second law of thermodynamics, which states entropy, a measure of disorder, always increases over time. A white hole's sudden, organized ejection of matter would be like watching a shattered glass leap back onto a table and reassemble itself. For this reason, most physicists argue white holes can't form naturally after the universe's initial conditions. They'd either need to exist from the very beginning or emerge as the final act of an evaporating black hole, a last gasp of stored information returning to the cosmos in a burst of radiation. The math gets even stranger when you consider quantum effects. If a black hole's singularity doesn't destroy information but instead encodes it on the event horizon, as the holographic principle suggests, then a white hole might be how that information gets returned. Imagine a black hole aging for eons, slowly leaking Hawking radiation, until it reaches a point where the radiation isn't just escaping but rebuilding what fell in. The result, a white hole belching out a scrambled but intact record of everything it once consumed. Of course, the big question remains: do white holes actually exist? No observational evidence supports them yet, and many scientists consider them mathematical curiosities rather than physical realities. But their possibility lingers, a ghostly reminder that the universe's rulebook might still have chapters we haven't read. Whether cosmic fountains or relics of the Big Bang, white holes challenge our understanding of time's arrow and hint that the cosmos might not just move forward, but in ways we're only beginning to imagine. At the tiniest scales of the universe, time might not flow like a river. It could stutter, flickering in and out of existence like frames in an old movie. This startling idea comes from the quest to merge quantum mechanics with gravity. two pillars of physics that stubbornly refuse to play nice. Quantum mechanics rules the microscopic world, where particles pop in and out of existence, and reality is a game of probabilities. Gravity, described by Einstein's general relativity, shapes the cosmos on grand scales, bending spacetime itself. But when you zoom in to distances a million billion times smaller than an atom, a realm called the Planck scale, these theories clash violently, and time itself might shatter into fragments. Picture this: if you could peer down to scales of 10 to the minus 43 seconds, time might not be continuous anymore. Instead, it could be granular, made up of indivisible time atoms that tick in discrete jumps, like the second hand on a clock that only moves in sudden leaps rather than sweeping smoothly. These hypothetical instants, Planck time, would be the smallest meaningful increments the universe allows. Nothing could happen in less time, because at these scales, the very concept of before and after starts to unravel. It's as if reality itself has a frame rate, and below a certain threshold, the cosmic film breaks into still images. Why would time behave this way? The answer lies in the chaotic quantum foam, a seething froth of spacetime predicted by theorists like John Wheeler. At Planck scales, the fabric of reality isn't smooth. It's a turbulent sea of virtual black holes and wormholes, constantly forming and vanishing. Gravity becomes so wild and unpredictable that spacetime loses its usual shape, twisting into knots that might sever the smooth flow of time we take for granted. In this maelstrom, time could become pixelated, with each pixel representing a frozen snapshot of the universe, stitched together in a way that only appears continuous from our macroscopic perspective. This isn't just philosophical musing. Some models of quantum gravity, like loop quantum gravity, explicitly predict that spacetime is woven from finite, interlocking loops, a cosmic mesh where time advances in quantum jumps. Similarly, string theory suggests that at the smallest scales, time might emerge from the vibrations of unimaginably tiny strings, flickering in and out of phase like instruments in an orchestra tuning up. Even black holes hint at this discreteness. When matter falls into one, its information gets smeared across the event horizon in discrete bits, suggesting spacetime itself might be built from fundamental units, like a digital image made of pixels. The implications are staggering. If time really is granular, then the smooth, unbroken passage we experience is an illusion, a trick of scale, like mistaking a movie's flickering frames for fluid motion. More provocatively, if these time atoms can be manipulated, it might open the door to quantum leaps through time itself. Imagine a future technology that could hold a Planck-scale time unit, freezing it like a paused frame, or jump ahead by skipping intervals like a needle hopping across a record. Time travel wouldn't require warping spacetime on cosmic scales. It could be as simple in theory as hacking the universe's base code, rewriting the sequence of time's pixels. Of course, we're light years from proving any of this. Probing the Planck scale would require particle accelerators the size of galaxies, or sensors delicate enough to detect the faintest whispers of quantum foam, far beyond today's technology. But the mere possibility reshapes how we think about time's nature. It suggests that beneath reality's smooth surface, time might be as bumpy and unpredictable as a dirt road, with potholes and jumps we're only beginning to map. And if that's true, the universe's clock might not tick the way we think. It could stutter, skip, or even, under the right conditions, rewind. The Bootstrap paradox isn't just a brain teaser. It's a cosmic riddle that unravels our most basic assumptions about cause and effect. Imagine discovering a groundbreaking theory in a dusty old book, only to realize decades later that you were the one who originally wrote it, after being inspired by that very same book in your youth. Where did the idea come from? Who truly invented it? This is the essence of the Bootstrap paradox, a loop where information or objects exist without any clear origin, like a snake swallowing its own tail. Let's break this down with music, a favorite example among physicists. Suppose a time traveler brings back Beethoven's Fifth Symphony to the 18th century, handing it to a young Beethoven himself. The composer, dazzled by the masterpiece, copies it note for note and publishes it as his own work. Centuries later, the same symphony is taken back in time again, repeating the cycle. The music exists, but its creation never actually happened. It's a closed loop, self-sustaining and eerily devoid of a starting point. The question isn't just philosophical, it strikes at the heart of how we define reality. If time loops are possible, does every idea, every invention, even every particle need a true origin, or can things simply be because they always were? The paradox gets thornier when applied to real physics. Quantum mechanics already allows particles to briefly borrow energy from the vacuum, violating classical causality on microscopic scales. Could macroscopic information like a symphony or a scientific theory similarly bypass the need for an origin? Some interpretations of quantum theory suggest yes. In the transactional interpretation, waves of probability travel both forward and backward in time, handshaking to create observable events. In this view, a bootstrap loop might not be a paradox at all, but a natural consequence of time's symmetric physics. The universe wouldn't need to explain where the information came from. It would just balance the books across time's flow. But there's a catch. If bootstrapped information has no origin, it raises unsettling questions about free will and creativity. Are our greatest breakthroughs truly ours, or echoes from futures we haven't lived yet? And how would such loops even begin? One theory posits that tiny quantum fluctuations, random blips in the fabric of reality, could seed these loops, magnified by time travel into coherent patterns. Another suggests that parallel timelines might bleed into each other, loaning information that never needed to be created. The bootstrap paradox forces us to confront a profound truth. Our linear view of cause and effect might be a comforting illusion. In a universe where time can twist into knots, some things might not have beginnings or endings, just endless, intricate dances where every step depends on the one before it and the one after. Whether these loops are possible hinges on the deepest mysteries of physics, but their very conceit expands our imagination. After all, if a melody can exist without a composer, what else might be waiting, timeless and uncreated, in the folds of reality? Most black holes are imagined as inescapable traps, their singularities hidden behind event horizons like prisoners locked behind iron bars. But nature has a twist. Enter the Kerr black hole, a cosmic whirlpool where rotation warps the rules entirely. Named after mathematician Roy Kerr, who solved Einstein's equations for spinning black holes in 1963, these objects defy the static doom of their non-rotating siblings. Instead of a point-like singularity at their core, Kerr black holes harbor something far stranger, a spinning ring of infinite density. And if you approach this ring just right, the equations suggest you might slip through it, not into oblivion, but into another universe or a different time. Here's how it works. A Kerr black hole spin stretches the event horizon into two distinct surfaces, an outer boundary we're familiar with and an inner, Cauchy horizon, where time and space trade places. Between these horizons lies the ergosphere, a region where spacetime itself is dragged around the black hole like taffy, twisted by a cosmic hand. Within this turbulent zone, the ring singularity waits. Unlike the crushing point of a static black hole, the ring's centrifugal force creates a repulsive effect at its center. The math reveals a mind-bending possibility. If you could navigate the intense tides and radiation, passing through the ring's center might transport you to a negative universe where time runs backward or physical constants are inverted. But the wildest prediction emerges when a Kerr black hole spins fast enough. At near maximum rotation, the inner horizon and outer horizon could merge, or even vanish entirely, leaving the ring singularity exposed. This is the infamous naked singularity, a gravitational anomaly without an event horizon to shield it from the outside universe. Einstein's equations allow for such objects, but their existence would upend everything we know about cosmic censorship, the idea that singularities must always be hidden. A naked singularity wouldn't just bend spacetime, it would tear it open, offering a visible gateway to other realities or timelines, the catch surviving the trip. Even if a naked singularity exists, the region around it would be a storm of quantum chaos and infinite tidal forces. Radiation from infalling matter would blue-shift to lethal energies, and the Cauchy horizon might act like a wall of fire, vaporizing anything that approaches. Yet some theorists argue advanced civilizations could harness these properties. A sufficiently nimble spacecraft, riding the ergosphere's currents like a surfer catching a wave, might skim energy from the black hole's rotation or use frame dragging to slingshot around the singularity without crossing the point of no return. The implications are staggering. If black holes or naked singularities exist, they wouldn't just be cosmic curiosities. They'd be natural time machines forged by the universe itself. No exotic matter, no wormholes, just the raw distortion of spacetime spun into a ladder across epochs. Of course, we've never observed a naked singularity, and many physicists suspect quantum gravity effects would prevent their formation. But the mere possibility forces us to wonder, could the cosmos be littered with these spinning doors waiting for someone or something to turn the handle? Pulsars are nature's most precise timekeepers, cosmic lighthouses spinning at dizzying speeds, beaming radiation across the galaxy with a rhythm so regular they rival the most accurate atomic clocks on Earth. But what if these stellar metronomes aren't just keeping time? What if their steady pulses are hiding something far stranger, subtle distortions that betray the presence of time travelers or ripples in spacetime itself? That's the daring premise behind the pulsar time machine hypothesis. Picture a pulsar's beam sweeping past Earth like the ticking hand of a colossal clock. For decades, astronomers have relied on these celestial ticks to test general relativity, detect gravitational waves, and even navigate spacecraft. Their predictability is legendary. But imagine if one day a pulsar's rhythm stuttered not randomly, but in a pattern that couldn't be explained by known physics. A sequence of delays or accelerations so precise it resembled a coded message. Or pulses arriving before they should, as if the signal had taken a shortcut through warped spacetime. This could be the signature of a time loop or a deliberate manipulation by a far future civilization using pulsars as interstellar telegraphs. The theory hinges on pulsars' near-perfect stability. If an anomaly appeared, say, a pulse arriving a microsecond early, it might not be a glitch but evidence of a microscopic wormhole bending the signal's path. Alternatively, a repeating pattern in the timing residuals could be a beacon, intentionally engineered by time travelers to mark safe corridors through folded spacetime. Some physicists speculate that advanced beings might even paint messages onto pulsar signals by artificially altering their rotation, embedding data in the gaps between pulses. After all, if you wanted to broadcast a message across millennia, a pulsar's billion-year lifespan makes it the ultimate cosmic billboard. Skeptics argue that natural phenomena like pulsar glitches or intervening dust clouds could mimic these effects. But proponents counter that certain patterns would defy conventional explanations. Take a sequence of pulses spelling out prime numbers or a signal that changes in ways mirroring human technology's evolution. Even more intriguing, if a pulsar's timing anomalies preceded a major astronomical event like a supernova, it could suggest a warning from the future, encoded in the fabric of time itself. The real test lies in the data. Projects like the Parkes Pulsar Timing Array already monitor hundreds of pulsars, hunting for gravitational waves. A deliberate search for temporal anomalies could uncover deviations too precise to be random. And if we ever found a pulsar whose pulses aligned with, say, a future Earth calendar, the implications would be staggering. It wouldn't just prove time travel is possible. it would mean someone or something is using the stars to speak across the ages. Until then, every flicker of a pulsar's beam carries a tantalizing question. Is this just physics as usual, or the faint echo of a civilization mastering time itself? We've all heard dark matter described as the universe's invisible scaffolding, an enigmatic substance that doesn't emit light yet shapes galaxies with its gravitational pull. But what if its influence goes deeper, twisting time itself into uneven currents? Imagine a galaxy not just as a collection of stars, but as a colossal time distortion field, where dark matter's gravitational tides subtly alter the flow of moments. This isn't science fiction, it's a tantalizing possibility emerging from the interplay of relativity and cosmology. Einstein taught us that gravity slows time. The stronger the gravitational field, the more time drags. We see this on Earth with GPS satellites, where clocks tick faster in orbit than on the ground. Now scale that up to a galaxy's dark matter halo, a vast, invisible sphere of matter weighing 5 times more than all the stars and gas combined. Its gravitational pull isn't concentrated in one place like a black hole's, it's diffuse, stretching across hundreds of thousands of light years. Yet even this gentle tug could create pockets where time flows infinitesimally slower than in the emptier voids between galaxies. Over cosmic distances, those tiny discrepancies might add up. A spacecraft orbiting a galaxy's outer dark matter fringe could, in theory, experience time slightly differently than one near the core, not by hours, but by fractions of a second over millennia. Here's where it gets wild. Dark matter isn't distributed evenly. Some galaxies have clumpy halos, others are smoother, and recent observations suggest there might even be dark matter, filaments weaving the cosmic web. These variations could create a patchwork of time rates across the universe, like a landscape of hills and valleys. But instead of altitude, the terrain is the speed of time itself. Areas denser with dark matter would act as subtle time sinks, while sparser regions would let time rush forward unimpeded. Could this be harnessed? Hypothetically, yes, if you could map the dark matter currents. A ship navigating the galaxy might chart a course through these invisible temporal gradients, surfing streams where time bends just enough to matter. Think of it like sailing. By catching the right gravitational wind, you could arrive at your destination not just across space, but slightly ahead or behind in time. The effect would be minuscule for any practical human lifespan, but for a civilization thinking in millennia, these nuances might be the difference between witnessing a star's birth or its supernova. The real mystery lies in how dark matter interacts with time's arrow. Most models assume it's passive, but what if it's dynamically entangled with spacetime? Some theories suggest dark matter particles could be relics from the early universe, carrying imprints of a time before time was fully formed. Others propose that dark matter's gravity might stabilize wormholes or other exotic structures, effectively pinning irregularities in time's fabric. If so, galaxies could be more than time distortion zones. They might be time's archivists, their dark halos preserving folds in history we've yet to decode. Of course, proving any of this is a monumental challenge. Dark matter refuses to interact with light or ordinary matter except through gravity, making it notoriously hard to study. But next-generation telescopes like the Vera Rubin Observatory could map its distribution with unprecedented precision, revealing whether those gravitational ripples align with subtle time warps. Until then, the idea lingers. The universe's missing mass might not just hold galaxies together. It could be quietly knitting time into shapes we're only beginning to sense. And if that's true, the cosmos isn't just expanding. It's breathing, pulsing in rhythms darker and deeper than we ever imagined. The grandfather paradox isn't just a thought experiment, it's a thorn in the side of time travel logic, forcing us to confront whether changing the past would unravel reality itself. But what if the paradox isn't a dead end? physicists and storytellers have proposed three compelling ways to sidestep it, each reshaping how we view causality. First, there's Novikov's self-consistency principle, which acts like a cosmic editor. Imagine traveling back to stop your grandfather's marriage, only to accidentally ensure it happens maybe by driving him into the arms of your grandmother while trying to intervene. The universe wouldn't let you create a contradiction. It would bend events to preserve the timeline you came from. This isn't just speculation. Quantum mechanics hints at similar feedback loops where particles adjust their behavior to avoid paradoxes, as if reality has built-in error correction. Then there's the multiverse solution, where every choice spawns a new reality. In this version, killing your grandfather doesn't erase you. It just branches you into a parallel universe where he died young and you never existed there. Meanwhile, the original timeline chugs on undisturbed. Think of 12 Monkeys, where the protagonist's efforts to alter the past only cement the events he tried to prevent. The film plays with the idea that time is a locked puzzle. Even your attempts to change it become part of its design. But in a multiverse, the stakes shift. Dark takes this further, weaving a tapestry of timelines where characters' actions don't rewrite history. They spawn new threads, each with its own tragic inevitability. The third fix is the predestination loop, where the past and future are locked in an endless dance. Suppose you travel back to give Shakespeare his greatest works, only to realize he'd always plagiarized them from you. There's no original creation, just an infinite cycle where cause and effect chase each other's tails. This isn't just a narrative trick. Certain solutions to Einstein's equations allow for closed timelike curves where events must repeat perfectly. The universe becomes a Möbius strip with no beginning or end to the chain of events. Each resolution offers a different lens on time's flexibility or its stubbornness. Novikov's principle suggests the universe enforces order, the multiverse dodges consequences by splitting realities, and predestination loops argue freedom might be an illusion. The chilling takeaway, whether through physics or fiction, the grandfather paradox doesn't just ask if we can change the past. It forces us to ask, would we even recognize time's rules if we tried? What if some particles aren't just fast, they're impossibly fast, moving faster than light and by extension backward through time? Enter tachyons, hypothetical particles that defy Einstein's cosmic speed limit, not by breaking physics but by bending its rules. These aren't just theoretical curiosities, they're mathematical specters haunting the edges of relativity, offering a bizarre loophole where cause and effect might not just bend but reverse entirely. The idea comes straight from Einstein's own equations. Special relativity states nothing with mass can accelerate to light speed, but it leaves the door open for particles that always travel faster. Tachyons, named from the Greek word for swift, would be born faster than light, their energy decreasing as they speed up, an eerie inversion of normal physics. Stranger still, their existence would warp causality itself. A tachyon emitted from Earth to a distant star could, from certain perspectives, arrive before it was even sent, effectively traveling backward in time. Imagine a letter that reaches its destination the day before you mail it, or a signal that echoes into the past. But why haven't we found them? Decades of experiments, from particle accelerators to cosmic ray detectors, have turned up empty. Some physicists argue tachyons are mathematical artifacts akin to dividing by zero, technically allowed by the equations but physically nonsensical. Others suggest they might exist but be inherently undetectable, either because they decay instantaneously or interact with ordinary matter in ways we can't observe. There's also the causality problem. If tachyons can carry information backward in time, they'd open the door to paradoxes like sending a message to your past self to avoid sending the message in the first place. Yet the idea persists, fueled by tantalizing hints. Quantum field theory allows for tachyonic fields, where particles briefly exhibit faster than light behavior during phase transitions. Cosmic inflation, the universe's exponential expansion in its first moments, might have involved something similar, with space-time itself outpacing light temporarily. Even string theory dances with tachyons, though often as unstable byproducts to be cancelled out by higher dimensional effects. The most compelling case for tachyons isn't in labs but in fiction, not as plot devices but as thought experiments. They force us to ask, if time's arrow isn't absolute, what else might be flexible? And if particles can dance backward through causality, could the universe somehow enforce consistency like Novikov's principle for quantum mechanics? Until we find proof, tachyons remain ghostly possibilities flickering at the edge of physics map, whispering that light speed might not be the final frontier, just the one we're stuck with for now. Crossing a black hole's event horizon was long thought to be uneventful, a silent, smooth passage into oblivion. But in 2012, physicists Ahmed Olmary, Donald Marolf, Joe Pulczynski, and James Sully shattered that assumption with a terrifying proposition. What if the horizon isn't empty? What if it's a seething wall of fire, an inferno of high-energy particles waiting to vaporize anything daring enough to approach? This is the firewall paradox, a quantum revolt that pits relativity against quantum mechanics in a battle over the fate of time itself. The conflict starts with Hawking radiation. As virtual particles pop into existence near the horizon, they steal energy from the black hole, slowly evaporating it. But here's the catch. Quantum entanglement demands that these particles remain linked to their partners inside the black hole. If the radiation carries information outward, as the holographic principle suggests, it must sever this entanglement, violating quantum laws that forbid such abrupt splits. To preserve consistency, the theorists argued, the entanglement must instead burn away in a cataclysmic release of energy right at the horizon. The result: a Planck-scale firewall hotter than the core of a supernova, annihilating any would-be time traveler before they could even glimpse the singularity. Yet this solution creates its own nightmare. Einstein's equivalence principle, the bedrock of general relativity, insists that crossing the horizon should feel like floating in free fall, no flames, no fireworks. A firewall contradicts this, implying that black holes have a detectable surface where physics as we know it ceases. Imagine stepping into what looks like empty space, only to be obliterated by forces you couldn't possibly anticipate. It's as if the universe posted a "keep out" sign at the edge of every black hole, enforced by quantum conflagration. Critics push back with alternative resolutions. Some propose that the firewall is an illusion, a trick of perspective like a desert mirage. An infalling observer might see nothing unusual, while someone watching from afar perceives the inferno, a cosmic version of whose reality is real. Others suggest the entanglement transfers smoothly to other particles, avoiding the need for fiery drama altogether. Then there's the even wilder idea that black holes don't evaporate linearly but shatter into disconnected spacetime fragments, carrying the information away like shards of broken glass. The firewall debate isn't just academic, it's a proxy war for deeper questions. Is spacetime fundamentally smooth or pixelated? Can quantum mechanics and gravity ever truly reconcile? And if firewalls exist, do they erase time travelers or encode their data into the radiation like a cosmic backup drive? The paradox forces us to confront the uncomfortable truth that at the edge of a black hole, our best theories clash violently, leaving the fate of anyone or anything venturing there hanging in the balance. One thing's certain, the universe's most enigmatic thresholds might not just bend time, they might burn it. Most time travel theories rely on cosmic heavyweights, black holes, wormholes, infinite cylinders. But in 1937, a relatively unknown physicist named Willem van Stockum stumbled upon a bizarre alternative. What if something as mundane as a spinning dust cloud could twist time into knots? His calculations revealed that under the right conditions, even ordinary matter in motion could warp spacetime enough to create closed time-like curves, paths where the future loops back to the past. No singularities, no exotic matter, just pure rotational energy sculpting time into circles. The key lies in frame dragging, that same phenomenon that makes Tipler's cylinder work, but here it's scaled down to something almost humble. Imagine a vast, dense cloud of dust particles, not a star or a black hole, just countless tiny grains all swirling together like a galactic whirlpool. As they spin, they don't just move through space-time, they drag it along with them like a spoon stirring honey. Van Stockham showed that if this cloud is massive and fast enough, the cumulative drag could become so extreme that space-time twists back on itself. Light cones, the paths light can take through the universe, tip until they intersect with their own past, creating a closed loop where cause and effect chase their own tails. Here's the catch: the cloud can't be stable. Left to its own devices, gravity would collapse it into a star or a black hole long before time loops form. But Van Stockham's insight wasn't about practicality, it was about possibility. His dust solution proved that closed time-like curves don't require infinite constructs or cosmic monsters. They could emerge from something as simple as matter in motion, if only for a fleeting moment. Modern refinements add layers to this idea. Some models suggest a rapidly rotating dust cloud could momentarily stabilize a time loop before dispersing, like a soap bubble shimmering into existence and popping just as quickly. Others propose that in higher dimensions beyond the four we experience, such structures might persist longer, hidden from view like shadows cast on a cave wall. There's even speculation that certain types of dark matter, if it interacts weakly enough to avoid collapse, could form Van Stockham-like configurations in deep space, invisible time machines humming silently in the void. The Van Stockham effect forces us to reconsider what's needed to bend time. Maybe the universe doesn't always demand black holes or warp drives. Maybe, under the right conditions, even the humblest whirl of dust could open a door to yesterday. It's a reminder that time's rigidity might be an illusion, waiting for the right twist to reveal its flexibility. And if that's true, the cosmos could be threaded with ephemeral loops, flickering in and out of existence too quickly for us to notice, yet proof that time travel might be woven into the fabric of reality itself. No cosmic extremes required. The quantum Zeno effect sounds like something out of a sorcerer's playbook. What if simply watching a particle could alter its behavior, even freeze it in time? Named after the ancient Greek philosopher Zeno of Elea, who famously argued motion is an illusion, this bizarre quantum phenomenon suggests reality itself might pause when under constant scrutiny. Here's how it works. Unstable particles, like radioactive atoms, decay unpredictably unless you measure them repeatedly. Each observation acts like a reset button, collapsing the particle's quantum state and delaying its decay. It's as if a ticking time bomb could be diffused indefinitely just by staring at it. But the real magic happens when you scale this up. Imagine a quantum system, say, a qubit in a supercomputer teetering between two states. Normally, it would flip randomly due to quantum fluctuations, but bombard it with continuous measurements and something extraordinary occurs. The system locks into place, trapped in its initial state as if time itself has stopped. Physicists call this quantum motionlessness, and it's not just theoretical. Labs have demonstrated it using lasers to repeatedly probe atoms, effectively halting their natural evolution. The implications are staggering. If observation can suspend time's flow for particles, could conscious observation do the same for larger systems? This is where things get speculative and fascinating. Some interpretations of quantum mechanics propose that consciousness plays an active role in shaping reality. In this view, the act of observation isn't passive, it's a creative force weaving possibilities into actualities. If continuous measurement can freeze quantum states, might a sufficiently focused mind, or advanced technology harness this effect to manipulate time on a macroscopic scale. Picture a futuristic time lens device that bombards an object with quantum measurements, slowing its local clock relative to the outside world. It wouldn't be time travel in the classic sense, but a form of temporal stasis, like hitting pause on a tiny pocket of reality. Skeptics, of course, dismiss this as a misreading of quantum weirdness. The Zeno effect, they argue, only works in isolated, microscopic systems where measurement doesn't disturb the environment, a far cry from the messy macroscopic world. Yet hints of macroscopic quantum behavior like superconductivity and Bose-Einstein condensates suggest the boundary isn't as rigid as once thought. And if entangled particles can span kilometers, why couldn't quantum observation effects scale up under the right conditions? The Zeno effect blurs the line between observer and participant, hinting that time might not be an indifferent river, but a dance where measurement, and perhaps even consciousness, sets the rhythm. Whether this could ever translate to human-scale time manipulation remains a tantalizing unknown, but the mere possibility reshapes a profound question. If watching a particle can alter its destiny, what else might our attention or our instruments shape without us realizing? Einstein's equations contained hidden threads, connections so subtle even he might have missed their full implications. Decades later, physicists Juan Maldacena and Leonard Susskind would tie these threads together into a radical idea. What if wormholes and quantum entanglement are two faces of the same cosmic coin? That's the essence of ER equals EPR, a theory suggesting that every pair of entangled particles, those spookily linked partners that influence each other instantly across vast distances, might be connected by microscopic wormholes threading through spacetime. Think of it like this: when particles become entangled, they don't just share information faster than light. According to ER equals EPR, they're literally stitched together by bridges so tiny they'd make a human hair look planetary. These aren't the traversable wormholes of sci-fi. They're more like quantum stitches in the fabric of reality. The math reveals something astonishing. The equations describing wormholes, Einstein-Rosen bridges, or and those governing entanglement, Einstein-Podolsky, Rosen, or EPR, are eerily interchangeable. It's as if the universe runs on two dialects of the same language, one geometric, the other quantum, both whispering the same truth. Deep down, space and connection might be inseparable. How could this possibly work? Imagine two entangled electrons. Measure one's spin, and the other instantly flips to match, no matter if they're light years apart. Standard physics says no signal passes between them, leaving us with the uncomfortable notion of spooky action at a distance. But ER equals EPR offers a visual. The particles aren't communicating, they're already touching through a wormhole too small to see. This bridge isn't a tunnel through space, it's a fold in spacetime itself, making what looks like separation from the outside a single, continuous structure on the inside. Black holes add another dimension. When two black holes become entangled, perhaps by forming from the same collapsing star, the theory suggests their interiors could be linked by a wormhole. That wormhole wouldn't let anything traverse it. Instead, it'd act like a quantum umbilical cord, ensuring their fates stay knotted. This isn't just abstraction. In 2013, physicists used holography, a tool mapping quantum systems to higher dimensional geometries, to show that entangled black holes in a theoretical toy universe shared spacetime bridges matching the ER equals EPR prediction. The math fit like a key sliding into a lock. Critics argue this might be a mathematical mirage, a clever analogy without physical reality. After all, no one's observed a wormhole, let alone a quantum-sized one. But supporters counter that the theory elegantly resolves two of physics' biggest headaches: how to reconcile gravity with quantum mechanics, and how to explain entanglement without magic. If spacetime and quantum connections are fundamentally linked, the universe might be far more interconnected than we ever imagined. What's truly mind-blowing is the implication. If every entangled pair is secretly joined by spacetime threads, the cosmos could be a vast, invisible tapestry of these microscopic bridges. Stars, planets, even you and I might be crisscrossed by hidden wormholes, remnants of ancient quantum handshakes woven into reality's fabric. It's a humbling thought that the bonds holding particles together might also be the stitches holding spacetime itself. The predestination paradox is the ultimate cosmic prank, a cruel twist of fate where every attempt to change history only locks it more firmly into place. Picture this: you travel back in time to stop a devastating plague, only to discover that your very presence spreads the pathogen you sought to contain. Or worse, like in The Terminator, where Kyle Reese's mission to protect Sarah Connor unwittingly ensures the birth of John Connor, whose future rebellion triggers Skynet's creation in the first place. The harder you fight the timeline, the tighter its grip becomes, weaving your actions into the fabric of history as if they'd always been there. This isn't just a storytelling device, it's a real philosophical and physical conundrum. The paradox forces us to confront whether free will is an illusion if every choice we make was always destined to happen. Einstein's equations allow for closed timelike curves where cause and effect loop back on themselves seamlessly. In these loops, events don't just happen, they're required. Take the classic self-created knowledge scenario. A scientist receives a cryptic equation from an anonymous benefactor, spends years decoding it, and finally publishes it as a groundbreaking theory, only to later travel back in time and deliver that same equation to their younger self. The equation has no origin, it's a closed circle of discovery without a creator. Physics offers eerie parallels. Quantum mechanics shows particles influencing their own past states in experiments like the delayed choice quantum eraser, where measurements made now alter how a particle behaved earlier. It's as if reality insists on consistency, retroactively adjusting events to avoid contradictions. The universe might operate like a grand, self-correcting script where time travelers aren't rebels breaking the rules, they're unwitting actors playing their assigned roles. But here's the haunting question: if the past is immutable, why does it feel like we have agency? The answer might lie in perspective. From inside the loop, every decision feels real and voluntary. Only from a God's eye view does the inevitability become clear. It's like watching a film for the second time. The characters don't know their fates are sealed, but you do. The predestination paradox doesn't just challenge time travel, it forces us to ask whether our lives are stories already written, or if the pen is still in our hand. And that uncertainty, that's the true spine of the mystery. Black holes aren't just cosmic vacuum cleaners, they might also be nature's ultimate time telescopes, bending light so severely that they offer a direct window into the past. Imagine an advanced civilization perched near a supermassive black hole, not to harness its energy or dive into its depths, but to turn it into an astronomical observatory unlike anything we've ever conceived. Here's how it would work. As light from distant stars and galaxies skirts the black hole's event horizon, it doesn't just bend, it loops. Photons that would have otherwise continued into the void instead spiral around the black hole in tight orbits, some completing full loops before escaping back toward the viewer. This creates a phenomenon called a photon sphere, a shell of trapped light where images of the universe are folded, magnified, and replayed like echoes across time. The implications are staggering. A civilization with the technology to decode these twisted light paths could effectively peer around the black hole, capturing light that's been circling for years, centuries, or even millennia. It's like standing in a hall of mirrors where every reflection shows a different moment in history. For example, light from Earth that grazed a black hole 2,000 light-years away would just now be completing its loop, meaning observers there could witness the rise of the Roman Empire playing out in real time, not as a reconstructed image, but as actual photons emitted 2 millennia ago. The black hole becomes a cosmic DVR, storing snapshots of the universe's past in its gravitational grip. But why stop at passive observation? A sufficiently advanced society might manipulate the black hole's spin or tune their detectors to specific light frequencies, effectively scrolling through historical events like flipping through pages of a book. Gravitational lensing around rotating black holes, black holes, could even split light into multiple images, each showing the same event from slightly different angles or times. Think of it as having a dozen camera angles on a pivotal moment in cosmic history, all captured by the black hole's natural distortions. Of course, there are hurdles. The light arriving from these loops would be faint, stretched, and scrambled by the black hole's extreme gravity. Decoding it would require computational power far beyond our current capabilities, not to mention a vantage point dangerously close to the event horizon. Yet, the underlying physics is sound. We've already observed gravitational lensing around galaxies, where massive objects bend and amplify light from behind them. A black hole would simply take this effect to its extreme, curving spacetime so sharply that light doesn't just bend, it folds back on itself. This hypothesis flips the script on how we think about time and observation. If civilizations could harness black holes as telescopes, they wouldn't just be studying the universe, they'd be rewinding it, peeling back layers of history written in light. And if multiple species across the galaxy are doing the same, the cosmos might be threaded with unseen observers, each peering into their own pocket of the past, silently watching eons unfold in the darkness. What if the arrow of time isn't just a one-way street? What if it flows in both directions, with the future reaching back to shape the past as surely as the past influences what's to come? This isn't just a poetic thought experiment. It's the heart of the Wheeler-Feynman absorber theory, a radical reimagining of how time operates at the most fundamental level. Picture a stone dropped into a pond, ripples spread outward, moving away from the source in expanding circles. That's how we usually think of cause and effect events in the present, sending influences forward into the future. But Wheeler and Feynman proposed something far stranger, ripples moving backward in time, perfectly cancelling out the forward-moving waves to create a universe where time is symmetric, a two-way conversation between past and future. At first glance, this seems to defy common sense. How can an effect precede its cause? The answer lies in the behavior of light. In classical electromagnetism, when an electron accelerates, it emits radiation, a photon traveling outward into the future. But the math also permits a bizarre alternative. The electron could absorb a photon from the future, a wave traveling backward in time to meet it. Wheeler and Feynman showed that if you account for all possible interactions, the forward waves radiating out and the backward waves converging in, they cancel each other perfectly. The result, a universe where time's direction is an illusion, a side effect of how these waves interfere. It's like noise cancelling headphones for reality. The sound of time's flow emerges only because the bidirectional waves are perfectly out of phase. This idea isn't just mathematical sleight of hand. It offers an elegant solution to one of physics' nagging questions. Why does light behave as if it takes the most efficient path between 2 points? Feynman's later work on quantum electrodynamics revealed that particles do explore all possible paths, with those traveling backward in time contributing to the final outcome. The absorber theory takes this further, suggesting that the entire universe is a self-consistent network of these bidirectional interactions. Imagine throwing a ball and watching it fly forward, but from the universe's perspective, the ball's motion is also being pulled by forces from the future, ensuring it lands exactly where and when it should. Critics argue this interpretation smacks of retrocausality, an effect preceding its cause, but supporters counter that it's no weirder than quantum entanglement's spooky action. After all, if particles can influence each other instantaneously across space, why not across time? The theory even dovetails with the block universe model, where past, present, and future exist simultaneously like frames in a film strip. In this view, Wheeler-Feynman's waves aren't breaking causality, they're weaving it into a seamless whole where every moment is both cause and effect, beginning and end. The implications are profound. If time is symmetric, free will becomes a tangled knot. Are our choices truly ours or echoes of decisions yet to be made? Could the universe's fine-tuning the precise constants that allow life to exist be the result of future states, selecting the past that leads to them? And if waves from the future are constantly shaping the present, might we one day learn to detect or even influence them? The absorber theory doesn't just challenge our perception of time, it invites us to consider that the universe might not move forward at all, but simply vibrate, with every moment eternally balanced between what was and what will be. The Boltzmann brain paradox asks a question so unsettling, it makes time itself feel like a fleeting illusion. Imagine a single, self-aware consciousness, a lone brain with false memories of a past that never existed, spontaneously forming from random quantum fluctuations in an otherwise empty universe. According to the laws of statistical mechanics, given enough time, even the most improbable events become inevitable. In an eternal or infinitely vast cosmos, the odds suggest such disembodied minds should outnumber ordinary brains like ours by an unimaginable margin. So why does reality feel so stable and continuous? Why aren't we all just momentary flickers of thought in the void? This paradox ties directly to time's most elusive mysteries. If consciousness can arise from chaos without cause or history, then our entire perception of a linear timeline, our memories, our sense of past and future might be a fragile illusion. The Boltzmann brain scenario suggests that at any moment you could spontaneously emerge from the cosmic noise, falsely remembering a lifetime that never was, only to dissolve back into randomness an instant later. It's as if time isn't a river but a series of disconnected frames, with no guarantee the next one will logically follow. Some interpretations of quantum mechanics even flirt with this idea, proposing that reality constantly resets at the smallest scales, with our smooth experience of time just a macroscopic averaging of these stuttering quantum jumps. Cyclical universe models deepen the strangeness. If the cosmos endlessly collapses and re-expands, Boltzmann brains might dominate the late stages of each cycle, when matter is sparse but time stretches toward infinity. In these eras, the probability of random consciousnesses popping into existence dwarfs the likelihood of orderly, evolved life like ours. That raises a spine-tingling question. If Boltzmann brains are statistically inevitable, how can we trust that we aren't one of them? The answer might lie in the anthropic principle, the idea that our very ability to ponder this question suggests we exist in a rare pocket of stability where coherent timelines persist long enough for complex life to arise. But the paradox doesn't stop there. Some physicists argue that if the universe cycles eternally, Boltzmann brains could become time travelers of a sort. A fluctuation with false memories of the future might remember events that never occurred in the previous cycle, effectively creating information from nothing. It's a twist on predestination, not a loop where the future influences the past, but a cosmic dice roll conjuring fully formed narratives out of randomness. Even black holes play a role. Their singularities might spawn new universes or reset the arrow of time, making Boltzmann fluctuations not just probable but necessary features of a self-repeating cosmos. The chilling beauty of this idea isn't just its challenge to time's continuity, but its subversion of reality itself. If consciousness can bubble up from the void, then every moment carries the potential to be the first or the last, with no past or future to anchor it. Yet here we are, convinced of our history, planning for tomorrow. Perhaps that's the ultimate testament to time's resilience, not as an unbroken thread, but as a story so compelling, even the universe insists on telling it. What if everything we think we know about time is just lines of code in an unfathomably advanced simulation? The simulation argument, first seriously proposed by philosopher Nick Bostrom, suggests our entire universe might be an artificial construct, a digital reality created by some higher civilization. If that's true, then time as we experience it could be nothing more than a variable in a cosmic program, something that admins could tweak, rewind, or fast-forward with the ease of a programmer adjusting a clock speed. Time travel in this scenario wouldn't require wormholes or warp drives. It might just be a matter of accessing the right cheat codes. Think about video games for a moment. In a virtual world, players often manipulate time without breaking a sweat. Save points let you redo mistakes, speedrunners exploit glitches to skip entire levels, and modders rewrite the rules to let characters move backward through the narrative. If our reality operates on similar principles, then the laws of physics, Einstein's relativity, quantum mechanics, might just be the simulation's operating system, constraints that could be bypassed by whoever holds the controller. The admins could pause the simulation to fix bugs, roll it back to a previous state, or even run multiple versions simultaneously like parallel save files. This idea isn't as far-fetched as it sounds. Quantum mechanics already hints at reality's fuzzy, probabilistic nature. Particles exist in multiple states until observed, as if the simulation is optimizing processing power by only rendering what's necessary. Glitches in our own world, like déjà vu or unexplainable synchronicities, could be artifacts of the system, temporary lags or patches being applied behind the scenes. Even the Mandela effect, where large groups misremember historical details, might be evidence of timeline adjustments, like a developer tweaking a game's lore between updates. But here's the twist: if we're in a simulation, time travel might not be a feature, it could be a bug. Imagine a rogue AI or a curious user exploiting a vulnerability to jump between epochs, leaving anomalies in their wake. This could explain historical accounts of inexplicable technology or prophetic visions not as folklore, but as literal backdoors in the code. Ancient civilizations spoke of gods manipulating time. In a simulated reality, those gods might just be players with admin privileges. The real kicker: if time is programmable, our attempts to understand it through physics might be like a video game character trying to deduce the rules of the engine from inside the game. No matter how brilliant our theories, we could be missing the bigger picture, that time isn't a fundamental force but a user setting. And if that's the case, the key to time travel might not lie in a lab, but in uncovering the hidden commands that let us whisper to the system itself. Whether you find this idea thrilling or terrifying, it forces us to rethink not just time, but the very nature of existence. If the universe is a simulation, then every moment is both infinitely precious and eerily ephemeral, a fleeting render in someone else's grand experiment. And if we ever do crack the code, we might discover that the greatest journey isn't through space, but through the source. From wormholes threading the cosmos like hidden passageways to quantum loops where particles rewrite their own past, we've journeyed through some of the most mind-bending ideas in physics, theories that turn time from a rigid arrow into a tangled web of possibilities. Black holes stand at the heart of this mystery, warping spacetime so fiercely that even light can't escape their grip, let alone our understanding. They're not just cosmic vacuum cleaners. They're time machines in disguise, where moments stretch into eternities and the past might collide with the future in a storm of singularity. Consider the sheer audacity of these theories. Quantum entanglement suggests particles might whisper to each other across time as easily as space, while the holographic principle rewrites reality itself, proposing that everything we see, every star, every galaxy, even the flow of time, could be a projection from a two-dimensional surface. And then there's the wild card, the simulation hypothesis, where time isn't a fundamental force but a line of code, waiting to be debugged or rewound by some unfathomable programmer. Yet for all their strangeness, these ideas share a common thread. They reveal time as something far more malleable than we ever imagined. Whether it's the closed loops of a Tipler cylinder, the paradox-busting branches of the multiverse, or the eerie symmetry of Wheeler and Feynman's time-slipping waves, each theory peels back another layer of the universe's deepest riddle. And at the center of it all, black holes, those cosmic enigmas that don't just bend time, they shatter it, leaving us to piece together the fragments. So here's the real question. Which of these theories left you questioning everything? Was it the holographic universe where reality might be a shadow on a distant wall? Or the Boltzmann brain, a fleeting consciousness conjured from the void? Drop your thoughts in the comments, and if you're hungry for more mysteries, hit subscribe. The universe is stranger than fiction, and we're just getting started.